welcome to the Astronomy seminar. Today's presenter is Sven Põder from Tallinn, and I need more thorough introduction for Maria.
Sven Põder. He's a PhD student from Tallinn University. He did his master thesis also from Tallinn University. So he recently published his second paper, what was the result of the master thesis, and I presented this paper in the journal club, previous journal club. And today he is extremely good at programming. So yeah. Sorry, I did not prepare. Are we gonna recording?
Yeah.
So, Sven, something else should I say?
I think it's good.
He plays guitar.
Yes, that was the last.
So.
Thank you both for the introductions. So yes, I'm Sven Põder, my supervisors are Maria Benito and Joseph Pata. And today I'm here to talk about accelerating data analysis with GPUs. And I will be using a case study of our project with Gaia Data, how this can be done practically. So first, I will be talking about GPUs in general and the GPU computing and its benefits. And then I will introduce a Python library called CuPy, which is a very powerful tool to easily implement GPUs into your data pipelines. And programming is quite boring for a lot of people. So what's even more boring is just talking about programming. I will try to introduce or show concrete examples how this can be done using a notebook that I made for this presentation. So hopefully this isn't going to be just words and everything will stay how it is and will work, including my own notebook. But okay, I will, alongside this, I will talk about some best practices for preparing code to run on GPUs. And then in the end, I will talk about handling Gaia data and how we made everything work for us. So it's going to be based on that example. So first, I will talk about the GPUs in general. So GPUs, or graphics processing units, are specialized hardware that are meant to handle very parallel workloads, and they're originally they were designed for rendering graphics for your computer, but because they can handle these parallel workloads very well, they have people are now using them for general scientific computing tasks. So a lot of machine learning, or most machine learning, is done on GPUs because you need something parallel to get this kind of data throughput. Otherwise, these projects would be impossible or would take very long. So machine learning is but one example. So there are others. They're used in molecular dynamics, galaxy simulations, everywhere. And they're very good at particular tasks. So not everything imported to a GPU works very fast, but they're good at tasks which involve, for example, linear algebra operations, or matrix operations, so convolutions and that kind of stuff. And they're also used because they're more power efficient and cost efficient than CPUs. So to delve a bit deeper into the difference between CPUs and GPUs, this is the only slide that I have of the architecture, so I'm not going to go into all the nuances. I'm just going to be talking briefly what are the main differences. So CPUs are designed to do one thing at a time. They have generally very high clock speeds, so they do things in serial, but they do it one at a time. Whereas GPUs they have more cores, they have smaller clock speeds, but because they have a lot of more cores, they can do stuff a lot more parallelly. So it makes up for that lack of clock speeds. So on the slide, you can see on the left is your typical CPU architecture, and on the right is a GPU. And on a CPU, you might have like 8 cores or something like this, but on a GPU, you would have thousands. So this is why they are very good for parallel computing. What's also good about GPUs is they have a lot more memory bandwidth. So when your CPU is fetching data from the RAM, it's going to be slower than a GPU fetching data from its video memory. So when you load data, say you have a lot of data, you move this data to a GPU and you want to do some calculations on it. So the way it fetches this memory from inside the GPU will be a lot faster. So this is why it's good for the big data sets. And if you have something to do with them, like, I don't know, matrix operations and stuff like this.
Yeah.
Yes.
So on the left figure, I understand each core has its own memory dedicated to data, this level 1 cache. So, but on the right dot, the GPU cores do not have each their own memory. It's shared somehow.
Yes, they have quite a different architecture. So there is also, they have this own, let's say, computing buses. So they don't have these kinds of L1, L2, and L3 caches separated through its cores. So they have, say, like, it's a bit difficult to explain, but dedicated shared memory locations, basically. So it's quite different.
Let me ask you something. What is cache? So that's the memory. The blue thing is the memory.
It's like a sidestep. So it loads some, like the CPU, for example, it loads some things into the cache so you can access it more quickly rather than just going to the DIMM RAM getting it. So the stuff it uses a lot or frequently, it loads into the cache, so it doesn't have to go very far to fetch it. So it's to optimize speed.
Memory within the processor.
So some takeaways from the introduction is the main things are GPUs are faster, a lot faster at certain tasks. So if we didn't use them, if we wouldn't use them in certain scientific computing tasks, lots of these projects would be unfeasible. So this is why they're used in deep learning. Also, I talked about this higher memory bandwidth, and what I also mentioned in the beginning is that they're quite power efficient and can reduce overall energy consumption and costs. They're also cost efficient in that sense when you take into account that they have a lot more performance. So when you compare, let's say, I don't know, the teraflops per second per dollar, these kinds of things. But all of you know, GPUs are actually quite expensive, so it doesn't seem very logical to say they were cost effective. But when you take into account that they have much higher performance, then it makes up for that. And what I want to also reiterate is that they are a great tool for very specific tasks. So if you have your Python codes, it doesn't mean if you port it over to a GPU, it will be a lot faster. So it has to be written in a certain way. So programming GPUs can be quite difficult. If, for example, on NVIDIA GPUs, you would use CUDA, which is the software platform developed by NVIDIA. And this is a C-like language, so it's not very easy to use. But to make GPU programming easier, we can use libraries like CuPy, for example, which is an open source library meant for GPU accelerated computing. And it's in Python. So Python is a very popular language. If you don't like Python, I'm very sorry. All of my examples are in Python. But it's a very convenient language to use. Using this CuPy library, for example, you don't have to know CUDA or go into, you don't have to define very specific memory routines and stuff like this. It kind of takes care of everything as it is built on top of CUDA. So it's like an abstract layer over it. So that's the thing. It's very simple and it's efficient when you want to do things quite quickly and you don't particularly want to waste a year or something to learn CUDA. And I also added on this slide the documentation and the main page. You can just find it by Googling. It's not hard to find. So the main features and advantages is that it supports NumPy-like syntax, and it's very similar to NumPy. you have ever used NumPy or SciPy. So they are the main computational libraries of Python. And if you know how to use NumPy or SciPy, then you're basically all set. So what you just have to change the library that you're using or the library name. It's almost the same. There are a couple of nuances which I will talk about. And also with respect to the functions and methods inside, so CuPy has almost all the same functions as you would have in NumPy. And so if you're doing simpler matrix algebra stuff, you won't have to implement any new things. It's got everything. And
so basically, if I define a numpy.array, instead of doing that, I will do CuPy.array.
Yes.
And define my array.
Yes.
To continue with my life.
Absolutely.
So I can simply do import CuPy as np.
Yes. You can do that. So actually declaring arrays is what I'm going to be talking about next. So okay, before that, I had some links on the slides, but in order to use this CuPy, so you need the dependencies are you need to have Python, which is a newer version of Python, 3.8 or newer. You need to have NumPy and SciPy, and then you also need the CUDA toolkit. If you have all of those, then you should be set. You also need an NVIDIA GPU.
You use CuPy to run code in NVIDIA GPUs.
Basically, yes. Technically, it's also possible to use it on AMD, but I'm not gonna bet my head on it because I've only used NVIDIA GPUs, so I don't want to. Yeah. Right. On to arrays. So, as Maria mentioned, it's it's the same thing as using NumPy. You just have to call CuPy instead of NumPy. And to look at the practical example, I have this notebook set up. I hope it is visible. Maybe I can zoom in. Right. Is this visible enough? Right. So this is running in my work desktop back in Tallinn, which is an NVIDIA GPU, which has 6 gigabytes of RAM. So I import both NumPy and CuPy here above. And here I define two functions where one uses NumPy to create an array, 3-dimensional array, and the other uses CuPy. So I define these functions so then I can benchmark them. So I can show you the difference in speed that it produces. So I also print out here the type, so you can see one is a NumPy in the array and the other is a CuPy in the array. So this is just an array filled with ones. This is on a GPU. It's the same syntax. Everything is the same. And I use Python's time library to basically time these functions. And it basically loops the same function that I defined and shows the average computation time. Hopefully everything works. So you see, the first one is defining an array on a CPU, and the second line is when using a GPU. So even just defining arrays is like 30 times quicker. So yes, if you're familiar with NumPy, then this should all be very familiar.
What is the window you are writing in?
This is VS Code, but I have my Jupyter notebook started from the VS Code. So this is actually just a library of code that we developed for the Gaia project. So if, for example, you would have multiple GPUs, then you have your GPUs in a cluster. They all have some IDs going from 0 to n, and then this is how you can move data from one GPU to another if you wish to do it. Now I will talk about some of the best practices, so to say, in writing code for GPUs, because even though you're using CuPy, the programming model can be a bit different, and also there are maybe some things that you're not used to when you're just writing code for the CPU. So
before you go into best practices, one slide before. So something I'm very confused. So I have my GPU and then I'm running with my GPU my code.
yes.
So and I just want to use one GPU. So I don't want to make this transfer from one GPU to another.
Mm-hmm. So
how do I know? Do I need to do some parallelization? So I don't know. So I want to do an MCMC. Or I want to do 100 calculations, let's say, of linear algebra, A plus B, 100 times.
Mm-hmm.
So do I need to split this 100 into all the cores that I have in the GPU, or if this is going to be done itself? You know what I mean?
Yes, for an MCMC, it might be even better if you have as a CPU separating all the the independent workers.
Yeah.
And then because the GPU is only good for a certain task. So if you have in your code, if you have some heavy lifting, some things that can work independently of each other, then it's good. So if you're talking about the piece of code where this can be done, then you can use GPUs. But if you have a lot of conditional code and branching.
But if I have an MCMC, so Western CMC, or let's not go to MCMC. Let's go, I want to do A plus B 100 times. They are all independent this 100 times. I'm going to calculate it in parallel in one GPU.
Yeah.
Do I need to write something like initialize some?
No.
So it's self going to do it for you?
Yes, you just define the arrays and then you add them together.
It's basically matrix operation. To define matrix with 100 or array with 100 elements, and then it's just this array operation, and this is done in parallel automatically.
Yes, I will also show an example how you can do precisely that.
But at the moment, all of this, the GPU is very effective when you have these arrays or matrices. But if you want to use something more complicated structure, then it's probably possible to use GPUs, but that requires much more effort.
Yeah, exactly. So it depends on what you want to do and how quickly you want to do it. So if you have time to invest in it, you can go into and write very complicated code for GPUs, or not. Depends on what you want. Okay. So I will quickly talk about some of the maybe unique concepts in GPU computing. So this with this slide, I mean that you have to really consider first what is your task that you're trying to solve before using GPUs. So you won't be porting unoptimized code to it. So if you have a lot of these conditional logic in your code and code that's very convoluted, then GPUs are not going to be your best choice. So before when you try to implement GPUs into your data pipeline, make sure that it is the right tool for the task. So it's not a miracle tool. This is the first thing to keep in mind. Also, it's important to use memory optimization. So basically, keep in mind that your GPU has limited memory, and you need to kind of take care how you load data into it and how you load data out of it. So
isn't the same for CPU?
Yes, because So a GPU, let's say, would have 6 or 8 gigabytes of video RAM. So you might not want to load everything into it at once if you have if you have a very large data set. So you can easily overload the GPU. So it's better to do it in batches. So this is what is done in deep learning. So common things that you might want to do is use smaller data types. So use float 32 instead of float 64, and reuse memory and avoid unnecessary memory allocations. And I will show examples of these in the Gaia data examples as well.
This is something that the library has to do. I mean, Python, you don't have direct control over memory anyway.
Yes, CuPy handles everything for you. So here, for example, I can show you how you can transfer data to and from the GPU. So I have the same functions as defined above. And if I do this, it creates an array on CPU. So this is a NumPy array. To port this, let's say you have this array in your CPU that you want to move to a GPU, then you do CuPy as array, and then it moves to the GPU. Here I also do some operation with it. I multiply each element in the array by 2, and then you want to move the arrays back from the GPU. Then you do CuPy as NumPy, and then, or you can just do xGPU.get like here. So this is how you move your data from the host, so the CPU, to the device, and it's as simple as that. But the overloading aspect, if you, for example, here I have this function that creates a 3-dimensional array, and we can actually see how much memory is being used in the GPU. So with this command NVIDIA SMI, you can see this GPU usage. Here you can see the memory usage. So 100 by 1000 by 1000 memory array is okay, but if I wanted to do something bigger, it's probably going to give me an error because I'm trying to overload the GPU. So let's try. Right, it gives you an out of memory error, and it says that it's way too many bytes to load to this GPU. So this is just a 6 gigabyte GPU. It's not very big. So this is what I mean by don't overload the GPU, and it has some kinds of limits. So, and this also goes with you should always try to minimize data transfers. So even though GPUs can give you incredible performance gains, when you're doing this back and forth with data transfers, this can be a big bottleneck. So you don't want to write something like which does many times it takes data from the CPU, puts it in the GPU, and then ports it back. You want to keep your data on the GPU for as long as possible. So, because in the CPU context, you have your data, let's say, loaded into a RAM. You have some, I don't know, pandas data frame, you have some star data. And then you move this to a GPU. So this process of moving from host to the device is quite expensive, and you don't want to do it when you can avoid it. So it's best to just move your data as much as you can to the GPU, and then only move it back or when you have the results. So this will make everything a lot faster, and then you won't have to deal with these kinds of bottlenecks. So other bottlenecks you can also identify. So you can use, there's tons of coding tools in Python. So you can use cProfile, and even in CuPy you have your a profiler. So when you write your code, it's very important to identify these bottlenecks and then remove them. in my examples, I'm using Timeit. So this is a very good tool for quick profiling. But for long-running programs, I recommend, for example, using cProfile. When you use cProfile, it gives you a summary of all the sub-processes that is going on in your program. So in this way, you can find the most heavy computing parts of the code. And the parallelization and performance optimization is one very crucial aspect before ever putting your GPUs to work. I would say it's about 70% of the work when you're using GPUs for computing is to make sure that all your code is as fast as possible before, and it's as parallel as possible. So, because in some cases, you can even have a worse performance on a GPU than a CPU. So the general recommendation is to use, for example, if you're using Python, to use NumPy, use all the NumPy syntax, and then use GPUs. So one example that I can show you is, for example, if you have a two-dimensional array, you want to do some addition. So you define your matrix, and the very naive version would be to just go iterate over the rows and columns. So this would be the slowest version. To do it in a NumPy-like way, you can just use NumPy sine and NumPy cosine functions on these arrays and then add them together, because NumPy then adds them element-wise. And then as a third function I have shown here is the GPU variant. So you notice here it takes the sine and the cosine of the matrices, and in the CuPy you have the same functions. So you don't have to change anything here. The only difference is this matrix is first defined on the CPU, so you need to convert this into a CuPy array. And then
my question is, why don't you input already a matrix that was already created in GPU?
Yeah, you can also do that. And it would make it faster. I will just put it to run because it can take tens of seconds. So it's this would be the recommended way to do it. This iteration over rows and columns, it makes everything slower. So you're not going to have a lot of performance gains over this. So you see the first simple iteration over lines and over the rows and columns takes 2.68 seconds. Then just by using NumPy, the power of NumPy, we have 50 milliseconds. And then doing the same thing on GPUs is even 15 times faster. But here you can see that the major performance gain was when just using NumPy how it's supposed to. And if I were to use this same logic here, where I iterate over all the elements, but do it on the GPU, it's going to take even longer, basically. So just on the CPU, it took 2.7 seconds, and on a GPU, it's going to run. So because you always have to keep in mind the special architecture of the GPU.
Question again. To do this matrix operation, you can scroll a little bit up.
Yeah.
This matrix equals CP minus matrix plus PP cosine matrix. So this, in actuality, would need 3 times the memory of our matrix. You have to keep that in mind.
You mean this particular?
Performing this operation, actually, it needs 3 copies of this array at the same time.
Yes, it loads them in.
Or even 4, actually.
So it loads in 1, and then it uses copies of the same array, and then but then it releases the memory again. But
yeah, but if you're working on the edge, you have a complex function, you can make like a nested function, but in that it can actually increase your memory requirement 10 times.
So
probably not too difficult.
It's not going to be as dramatic. So what NumPy does, it does everything, all this memory optimization, it does it for you. So when you're doing this, it's also doing some kinds of loops, but those loops are in C, and it is written, or NumPy is written in a way so you don't have to worry about these kinds of things. Oh no!
That's a mistake.
I moved this with my hand, but it's not even connected. Okay. I hope it's
not finished before to make it work.
It might be a sign that we started later, so it's after opinion. I think we started 15 minutes late, so it has to be finished 15 minutes earlier.
Maybe I can fix it like this. Okay. So okay, the projector started working again. That's good. Okay, we are back. Sorry. Okay, so yes, I don't know all the specifics of how NumPy works, but I know that they have some clever ways how to prevent this kind of doubling of data. So they have like different routines inside of it.
If C is running loop, then again you can access one element at a time.
Yeah. So
we can't see the share anymore.
Oh no, 1 sec. Thank you.
Yep, it's back.
All right. So we used GPUs to accelerate some data analysis on Gaia data. We used data from DR3, and we worked on a project that was sort of the aftermath of my master's thesis, which took quite some time. And it was interesting that at the end of the day, it was GPUs who came to help. I will be talking about mainly the data handling aspect of it. But I will also introduce some of the context of what the project was. So we wanted to calculate the circular velocity curve of the Milky Way, and then quantify uncertainties in a self-consistent manner. So we would take the rotational velocities from Gaia DR3, and then we would reconstruct the circular velocity curve using Bayesian inference. So using a Markov chain Monte Carlo algorithm to basically sample these circular velocities. And the error bars that we get out of the sampling, so estimate the uncertainties in the sun's galactocentric distance, for example, and the spatial kinematic morphology of the tracer stars. And the tracer sample itself was about 1.6 million RGB stars in the end, with all the 6-dimensional phase space coordinates. So this is the data that we were working with, albeit it's not catastrophically big. it's not small, but it's not, horrible. But because we have the data from DR3, so these are in the International Celestial Reference System, we need to first transform them into a galactocentric frame and cylindrical coordinates. And then after, we can get the circular velocities using the axisymmetric radial Jeans equation. So this seems simple enough. So what's the problem? The problem is that when you're transforming these phase-space parameters, this is essentially a series of matrix operations, right? But this takes too long because we wanted to use this in an MCMC. So, and also the covariance information propagation to the galactocentric frame takes even longer because with each star, you have your covariance information. So you construct for them the covariance matrix. And then you also need the Jacobian, which tells how to propagate these values to the galactocentric frame. So you need to generate the covariance matrices, you need to generate the Jacobian matrices, and then you need to multiply them, and then it's like a lot of matrix operations. So this all adds up in the end. And if you take this into account, that we're running this in an MCMC, so which may run for, 6 or 10,000 steps. At each step, you vary some input parameter, for example, the sun's galactocentric distance, and it needs to repeat this transformation for all the stars every time you modify this input parameter. So explain a bit better what I mean. So to go about this, you would get your input data from Gaia, then grab one star, transform this, while you're grabbing this one star, you also need to correct the transformation matrices. You generate the covariance matrices, and then you have the propagated covariance data, and then you repeat this over the data. So this is not an ideal way to go about it. And if you do something like this, then by the time it finishes, you will be much older. So this is not good. A better way is to use this array broadcasting with NumPy. Notice how I am not even talking about GPUs yet. So this is like the preliminary work you go through before you start using GPUs. So broadcasting is a mechanism where you can basically propagate one array over the other. So I added a very simple example on the slide. So when you have one array and then you multiply this with the scalar, so it kind of stretches itself over the whole array. So in the context of doing coordinate frame transformations, instead of doing like transformation over transformation, you have your Jacobian matrices in one array and then your data in the other, and then you can multiply together and it does it parallelly. And it's much faster. So at the end of the day, you would have your star data and then n times 6 by 6, whatever array, which contains on the transformation of Jacobians. So this broadcasting, it avoids unnecessary loops in the code. And what's one good thing about it is it makes the code more readable and concise. So this is also a very good aspect of it. So going back to the optimized data scheme, here I show basically the same data pipeline without this loop, but using array broadcasting. So first we have our input data. It goes into a NumPy array. You generate all the matrices, then multiply them together into the with the star data, and then generate the covariance matrices, and then basically multiply them together all at once. So this is the general idea. And even when you're generating these covariance matrices, it's very it's convenient, and it's good to use NumPy indexing. So basically avoid loops wherever you can. Use clever NumPy indexing, and then you can generate matrices very quickly, and you can multiply them very quickly. So this resulted in a very massive speed up already, but the MCMC was still running very slow. So this is where finally we implemented CuPy, and this was implemented after all the possible optimizations were done, and there was basically no more performance left to squeeze anywhere. So this would kind of like make it or break it, almost. But it was pretty easy to implement this CuPy into this kind of data pipeline. It took like a week or two at most. So this wasn't some meticulous, a year-long project to get this. It was basically, we had a nail, you have a hammer, you need to hammer it. So you don't care like what is the perfect alloy for the hammer or something like this. You just need a good enough hammer and you need to nail this. So in most cases, it was basically as simple as changing NumPy to CuPy, but the nuances were in the data transfer between the host and the device. Host is the CPU, device is GPU. So those were the only, let's say, modifications to the code, if I don't count just changing NumPy to CuPy. And also the data type was also put to float 32 instead of float 64, because GPUs work a lot better with 32-bit float. So I can show you examples of what this coordinate transformation looks like. So this whole window is basically my VS Code, where we have this Gaia data that's hosted on GitHub. And here I load in.
Just out of curiosity, what is disabled JIT?
So here, because we wanted to make this code a lot faster at all steps, we also used JIT compilation when when generating the Jacobians to transform the covariance matrices. Generating the Jacobians is quite an undertaking, because we needed to take all the derivatives with respect to the parameters analytically, write them down into code, and then it needs to create these Jacobians very quickly. So it's not a nice piece of code, and we made it faster by using JIT compilation, which does something like it's so you employ it on your functions, which are in a NumPy format, and then it compiles them. So at first it runs slowly, but once the code is compiled, the Python function, then it will run a lot quicker.
It's like CPython.
Yes, basically. So whenever this code is running on a CPU, I would use I would not disable JIT, and then it would be quicker. But JIT is not yet compatible with CuPy, I think, but I think it's an experimental feature. So that's why.
So that's why I was getting errors. That's why.
Maybe. So yes. So here I just set the device context. The device I have in my PC. I don't actually need to do this for this example. I also import pandas, and then there are these two modules which contain the different transformation constants to use in the coordinate transformation and the functions. So I have this data from our project, which is about 1.6 million lines. As I said, it's not very huge. So before transforming, I also declare a few parameters which describe the sun's position and velocity that we need to get the galactocentric frame. And here I have implemented a function where it transforms the coordinates in the International Celestial Reference System to the galactocentric using a CPU. Notice I have written it in a way where it's basically, you can just define either NumPy or CuPy, and then you feed this module to it, and it will automatically use either the GPU or the CPU. So this is 1.6 million stars about, and it takes about half a second. And then I do the same thing on a GPU. So as I said before, the data needs to be moved to a GPU. So I use CuPy as array. And then it's the same function, but here I'm using CuPy. And then I can time it. So it's 28 milliseconds. So it's about 10 times faster or. And the same thing I can do for covariance matrix transformation. So first I have a function which generates all the covariance matrices for all the stars. So it's 1.6 million stars, and each of them have a 6x6 covariance matrix. I get the galactocentric data on the CPU. And in this routine, what I basically do is I have the covariance matrices, I have the data in the from the Gaia and the galactocentric data. So I need to transform these matrices first into the galactocentric frame using Cartesian coordinates, and then these Cartesian coordinates are transformed into cylindrical ones. So there's two transformations. And this, in fact, was the most annoying part of the code because it took very long. It was a constant bottleneck every step of the way. So here I'm actually just showing in the slides as well the progression where I was learning different things about Python programming, and I was just implementing quicker and quicker solutions. And eventually it's gotten somewhere where you can get reasonable results. So on a CPU, it takes some time. Should take a few seconds, but when you're using timeit to time your functions, it does many loops with the functions and it gets you the average time result. So on average, this takes about 2-something seconds. But if you were to use a GPU, then it's basically the same function here as above, where I change the NumPy to a CuPy. And if I time this, it should give us better performance. Right, so about 160 milliseconds to do two transformations, first to the Cartesian galactocentric and then to cylindrical galactocentric. And it's doing this for 1.6 million stars. So they all have 6x6 matrices. The Jacobians are also 6x6. So it's doing Jacobian multiplied with the covariance matrix multiplied by the truncated. It's doing this for 1.6 million stars, and it's doing this for 2 times. And it does it in 160 milliseconds, which is pretty good. And so it turns out this was the missing piece of the puzzle, using GPUs to finally run MCMC in a time frame where we don't get zeroed. So we used MC, this library, to do the Markov chain Monte Carlo. And the final setup consisted of multiple CPUs and GPUs. I will also show kind of broadly how the data pipeline looked like. And we also use Python's multiprocessing module, which takes advantage of the CPU core allocation. So with multiprocessing, you can create multiple independent workers, which have different CPU cores. And we use this to basically split the workers in the Markov chain Monte Carlo. I will explain a bit about this on the next slide. And the GPU devices were basically used to do all the heavy lifting. So the transformation was done on the GPUs, but the Markov chain Monte Carlo basically worker management and sampling was done on the CPUs. And along the way, we made sure that we were reusing memory properly and minimizing these data transfers that I was talking about before. So the way you would do this is I constructed this scheme before doing any Markov chain Monte Carlo sampling. In order to reuse our memory and to take care of this memory optimization, we used in the end, we used 6 GPUs. So we would load the raw data that is not processed yet, the input data, we would load onto the CPUs and also the covariance matrices. So this is part of the data that you have to reuse along when you're doing your MCMC loop, right? So it doesn't make sense that in every sampling step, you load this data in, do the transformation, load this back, load this data in. So when setting up the MCMC, we load this data beforehand to the GPUs. So there, when it is used, or if you want to use it, it's already there. And this is static data as well, right? So to reiterate, what we were doing is we have this MCMC. At each step of the sampling, we would vary the parameters, theta on the slide. So the parameters would go into the likelihood function. In the likelihood function, we would use GPUs to transform the data. After this is done, we load them back to the CPU, calculate the likelihood, and then go on to the next step. And the CPUs themselves were divided in such a way so we could maximize the usage of multiprocessing. So multiprocessing was used in the MC library. So if we had 50 workers and 12 CPUs, each CPU would have 4 workers to deal with. So because workers are exploring the parameter space independently, we can split them along the CPUs, and each CPU is assigned a GPU ID. So this is like a queue is formed beforehand in order to work as efficiently as possible. So it's not going so each CPU has one specific GPU that they would be using at all times. So this is like an organized way to do this. So at the end, it turned out great. Because using only CPUs, each step of the Markov chain Monte Carlo took 10 minutes, and this was we didn't have time to wait for it. And also, if you have something that takes this long to complete, so imagine the MCMC had to run through thousands of steps. If something is broken in the code, which is something you should assume always, it's not a good idea. But using, for example, 12 CPU cores coupled with 6 GPUs, one single step was reduced to 11 seconds. And now the project is suddenly feasible. So at the end of the day, all this rigorous code optimization and setting up these pipelines work. And to basically summarize this CuPy implementation, I added to this slide the main ingredients to this CuPy. As the projector shuts off again. Let's see. Okay. Right. So basically, the 3 main things is to profile and optimize your code before using GPUs, just to make sure that there are no bottlenecks inside of it and everything is running smoothly already. Then also, when you're using CuPy, use NumPy syntax. So all the functions in NumPy that you can use them. So you can basically do a CuPy drop-in, replace NumPy with CuPy. The third is memory optimization. So that's the thing that I was talking about. You should minimize the data transfers between the CPU and GPU. So this ensures that you're using memory as effectively as possible, because GPUs don't have an infinite amount of RAM inside them, and it's quite easy to overload them. And with data and astronomy and astrophysics, it's not difficult to overload the GPUs. It's quite easy. So I get this back. Let me share the screen again. Right. Okay. And I would conclude my seminar like this, that GPUs can be a very powerful computational tool when processing very large data sets fast. And though generally GPUs are very difficult to program using software libraries like OpenCL or CUDA, we can make things a lot easier by using libraries like CuPy. And before using CuPy, make sure that you optimize your code well, that you profile it, that you find all the bottlenecks, and then you can make sure that your code accounts for the way that the GPU is designed. And what's very good about these libraries like CuPy and GPUs, they can make projects that are unfeasible at first, to make into realistic challenges, and they can be turned into achievable results. So with our example using Gaia DR3, just doing minor modifications to the code, doing extra work for a week or two, and then we can actually finish our project, which we couldn't before because it took so long. So I thank you for your time, and I'm ready for any questions if you have them. Thank you.
More questions? Comments?
Do you know something similar for Julia? So CuPy is similar to Julia.
I don't. I'm sorry.
MCMC implementation, therefore it's not good.
Sorry, say again.
So if I want to do MCMC implementations in GPU, so the last step of the project that you were using in multiprocessing for doing parallelization,
Yeah.
in principle I can do the same thing with GPUs.
Yes. Yeah. The easiest thing is to do is just to identify what's the, at the end of the day, you're going to be using CPUs and GPUs both. So
you think the goal is to use both things?
I think so. At the end of the day, you have to anyway use both. So because it's not like the GPU makes the CPU incomplete or unusable. It's that they excel at different areas, right? So the things that the CPU does best is best left to CPU, but things that are just boring, I don't know, matrix computations and multiplications that the GPU is designed to do should be ported to the GPU. So.
Question about the memory management and the bottlenecks. If I have a situation, if I load an array onto the GPU, it's accessible to all of those cores there, right?
Yes.
So if I now have a situation where I have a big static array that I load onto it, that has to be accessible to every processor, and at the same time, I have let's say, a long vector of quantities on which are independent and on which I want to do some computation, using this big static array. And then in principle, what I imagine would happen is that the long vector would be sort of split into parts, each one given to one processor, and now they do it stuff independently. But this computation needs at every step access to this big static array. And now if several processes are at the same time trying to access the same memory locations of the static array, does this cause a bottleneck? They don't modify anything in this list, but they need access to it.
So they want to, many sub-processes want to access the same memory location.
Yes.
I'm not sure if it would cause a significant bottleneck. To be honest, I'm not quite sure. But the good thing that this is what I was saying about the difference about CPUs and GPUs, that their memory bandwidth is huge compared to CPUs. So this shouldn't generally cause a problem.
Generate a situation where one process has to wait for the other.
Yes, because on a CPU, the way it grabs stuff from its memory is like, let's say on the order of 50 gigabytes per second, but on a GPU, it is already up to many hundreds of gigabytes per second, up to terabytes per second, because it has this point-to-point connection with the core, and it's much closer. So, I would say generally it didn't cause a problem, but then again, there are always these kind of nuances. It depends on what you're doing.
Let's say you have a process, like you have this big array, and you have multiple processes, and they run, say, a big array, a vector, and a bunch of processes. But inside the process, there is a condition that like accessing this large array is random, and it is conditional of the whatever it's calculating.
Yeah, it is.
Is it an optimal problem for the GPU or not?
Yeah. So anything that can be split into very parallel subroutines is a good problem for the GPU. So mainly, linear algebra operations, but everything that you can think of which can be split, which don't need to speak to one another is good. So you can just send it through and do it very fast.
Say, and you have an array, you have a vector, and now the process is the vector value is more than 0.5, you take sign of the specific array value and multiply the vector. It's low, you take cosine, and then split out the array.
What I do with this in this vector, basically I draw a random number, and based on this random number, I look up a value in this big array and use it to make a computation. But this happens independently for each of these values in the vector. But get to a situation where they want to access to.
But then it is an array operation. You can call this function on top of all your vector. If everything is independent.
So each element of the vector, if you draw a different
if everything is independent, you can use this vector as an argument for your function, for your button.
Yes, but what really happens is that the part, I mean, everything is independent except for this access to this one array, which I don't want to make copies for each process, right? So it's one array, and many processes want access at the same time.
Yeah,
and possibly at the same location within this array.
Yeah, the question if it would cause a bottleneck or not, I'm not quite sure. So I don't know.
What are the largest memory, biggest memory graphic cards that are available right now?
For example, in KBFI, or National Institute of Chemical Physics and Biophysics, we just had installed 2 new NVIDIA GPUs, one of which we got from the NVIDIA grant program for our work with Gaia Data. And these are NVIDIA 100 GPUs, and they have 80 gigabytes of video memory. So the general GPU, for example, would have like 6 or 8 today's NVIDIA flagships. But this has 80 gigabytes. So these are pretty much one of the biggest, let's say, heavy lifters on the market right now.
How much it costs?
a lot.
More than 6,000.
More, yes, upwards 10,000.
But compared to the CPU computer with like terabyte of memory.
Yes, that's the thing. It can have this terabyte of memory, right? But you have the 80 gigabytes, which has more bandwidth, which works faster.
Mhm.
So it's like a trade-off. You can have more RAM, but you have it work slower versus less RAM, but have it work faster. In any case, it should work very good.
And how many cores these GPUs have? Basically, if I have, let's say, an array with only 2,000 elements, is it sensible to run it on CPU? Or I don't know.
If you have 2,000 elements, you can run it either on CPU or GPU. But
Yeah, but
it's not very. That's not like horribly large, right? So a CPU will handle it also very good.
exactly. That's why I think that the data transfer will make it fluid at the end.
Yes, if you're doing lots of small processing or small routines, then it will make it slower.
So how big the array must be so it is? I think it's the same order as the number of cores in a GPU.
I'm not sure about that. It has to be larger than 2,000 for sure, but I don't think I have a concrete answer on what is the.
But how many cores
limit.
GPU have?
They have like thousands of different CUDA cores basically, but there's also like inner architecture, how each compute section is divided into like threads and blocks, and there's these nuances also. So you might have a core, but inside of it there's more sub processes going on. Yeah.
In Lumi, supercomputing, they are building CPUs and GPUs and
Oh,
so how many CPUs, how many GPUs?
in Lumi, I'm not sure. I haven't looked at their procurement sheet, but
That is, all supercomputers are built in both in CPUs and GPUs, or is it only particular to Lumi?
pretty much all of them. Yes, I think it's also a good idea. So if you want to do any kind of neural net training or deep learning, you will want to use GPUs because it gets you the fastest results.
Okay, so any questions online? You can speak or write into the chat.
So no questions.
Okay, let's thank the speaker again. Very interesting. Okay, there are lots to think.
Thank you for inviting me.